Okay, let's get started. So, um, last time we kind of finished with doing our little shortcut for doing the electron configuration. So, let's kind of take another look at the periodic table, and then we're going to kind of learn some of the reasons for doing all this stuff with electron configuration. Alrighty, let's see. Boop, 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 ta-da. Okay. Periodic table here. So let's go ahead and today we're going to kind of we talked about the periods yesterday, where those were the horizontal rows. So today we're going to talk about the columns, the vertical columns here. Those are going to be called groups. Those are going to be the columns there, and there's kind of two ways of talking about the groups. Some people will label them 1 through 8 like this. Sometimes you'll see 13, 14, 15, 16, 17, and 18, or something like 8A, 7A. It just kind of depends on your periodic table. But they're all similar, right? In here you'll have either 3 through 10, 3 through 12, or having 3B and stuff, and you'll have all these sorts of like crazy stuff going on for the transition metals. I guess we don't know what transition metals are yet, but we'll learn that right now. So we're going to have names for a lot of these groups. That's going to make it easy for us to kind of easily identify them. So, group 1, which is going to be our lithium, sodium, potassium, etc., cesium, rubidium. Group 1 are known as the alkali metals. So we don't include hydrogen with this group, because obviously hydrogen is not a metal. We're going to talk about metals later. But that's going to be the name of the first group. Our second group, which has beryllium and magnesium and calcium and strontium and barium and all those good ones, that's group 2. We call those the alkaline earth metals. Sometimes that hyphen is there, sometimes it's not. Doesn't really matter. If we skip ahead to the other side of the periodic table, going over here, the ones in purple, group 18 or 8A, are the noble gases. We're going to see later why the groups 1 and 2 are called alkali and alkaline earth in chapter 11, way down the line. Suffice it to say that they make basic things when they react with oxygen. The noble gases, though, are called noble because they are inert. They don't react easily. And we're going to see, of course, they're all going to be gases, hence noble gases. So we're going to see that all of these elements that we're going to look at will want to be like noble gases. Noble gases are kind of, the elite, of the periodic table. Everybody wants to be them. Anyways, continuing on here. If we look at group 17 or 7A, those are going to be the halogens. That name means salt forming. So those are going to be kind of the, sodium chloride, of course, is what we would think of as table salt. We've got chlorine in there. we're going to see that these elements will very commonly form ionic compounds. We'll talk about ionic compounds next chapter. And let's see, last color, what shall we use? How about orange? We have kind of the last group we're going to talk about. I don't even know what's under selenium. Group 16. Are going to be our chalcogens. Which I don't remember what that name actually means, but who cares? What's important to note about all of these is that all of our alkali metals are going to have electron configurations that end in S1. For our alkaline earth metals, those are going to end in S2. For our noble gases, they end in P6. And then the other two will have their own ones. We don't really have names for the other groups. In fact, chalcogens is not even very common to use. Usually just kind of these first four are more commonly used as names. People would just say group 17 or something also. That's pretty common. Okay, so we have a couple other distinctions to make here. In this middle area, the D block, we have what are called the transition metals. And those we're going to see have pretty interesting properties. That's where a lot of interest in chemistry is, because these metals do a lot of different things. We're going to see sodium is actually very boring as an element. It really does one thing and one thing only. But the transition metals kind of go crazy. And we're going to have entire sections of inorganic chemistry is all about transition metals. So if any of you go on to take more advanced chemistry, you'll spend time with the transition metals. Here we're not going to really focus on them that much, but that's okay. We're going to see that everything in the S and P block are called main group elements. Everything in the S and P blocks are called main group elements. And then I have omitted our poor F block down here. I'll just put it down here. We call those the inner transition metals. Again, those do pretty interesting things. That's where we have uranium and plutonium as well. Those are going to be inner transition metals. So that's that section that we kind of take out of the periodic table we put at the bottom. If we were to look at it, that's this stuff at the bottom here, where we have lanthanum and actinium going on through there. So that's our F block down there. That's where we're going to have the inner transition metals. Okay, back to this here. All this talk about metals and stuff. Let's go ahead and look at our periodic table again. Oops, not bromine, boron. Let's see, what is 14 silicon? Okay. We're going to see that the periodic table is further divided, and where we have this kind of line going along boron and silicon there. Some people draw it on the other side, doesn't really matter. We're going to see that everything along this line, we're going to see are going to be special. Those are going to be what are called semi-metals or metalloids. They're going to be kind of neither metallic nor non-metallic, but the rest of them, we're going to see everything on this side will be metals, and everything on the other side will be non-metals. And we can kind of give some information about metals and nonmetals, about their properties. Of course, the F block 2 are also metals. They're the inner transition metals, so they're certainly metals as well. So we can see right away, of course, most of the periodic table is made of metals. Most things are metal. And then we have a few nonmetals, and then even fewer semi-metals. So when we think of metals, probably a couple things come to mind. If you just think about metal, you probably say, okay, it's shiny, silvery, hard, dense, tough, like hard to break. These are typically malleable, which means we can flatten them. Like we can make aluminum foil pretty easily. We can make really thin sheets, like gold leaf or something. They're ductile, meaning we can make wires of them. We can stretch them really thin as well. Let's see what else we have. These are pretty conductive as well, both to heat and electricity. And we can kind of see that this is going to be, stuff that we already think about when we talk about metals. Like when we talk about, wires, of course, typically we use copper for wiring, right? We do it for these properties because it is ductile, it is conductive, and it's tough, So it can conduct our electricity, and we can make it into very thin things, so we can use less of the material to do that. Nonmetals, on the other hand, are going to kind of be the opposite of metals in most respects. They're often dull or colorful or colorless, depending. By the way, most metals are going to be solid. Mercury is kind of our exception to that. Mercury and some of the others like gallium and francium and cesium kind of could be liquid, just depends on what temperature you're looking at. But most metals will be solid. Our nonmetals are either going to be colorful or colorless. For example, sulfur is going to be kind of bright yellow, chlorine is kind of yellowish green, bromine is kind of this very vivid red-brown, iodine is purple, but all of our noble gases are completely colorless, so the point is they're just not silvery. They're everything else, basically. These are typically going to be not dense, so we're going to see a lot of them will be gases or liquids. There are some solids, like carbon, for example, definitely a non-metal. That is going to be a black solid. If they are a solid, they're going to be brittle, meaning that if you try and smash it, they will just completely break, like pulverize. So if you take a piece of charcoal and hit it with a hammer, it's just gonna, completely crumble. It's brittle. However, if you take a piece of metal, like another hammer, and smash it with a hammer, either nothing will happen or it'll kind of just bend a little bit. But you're not gonna shatter it into a bunch of little pieces. These are also going to be non-conductive. With a couple of exceptions. Certain what are called allotropes of carbon are conductive, like graphite. But by and large, most nonmetals are going to be non-conductive. And let's just put the word most here. And then, guess what? The semi-metals can be all of the above. In either case. Semi-metals can be conductive, they can be non-conductive, some are conductive in certain conditions. We're going to see that semi-metals are very important for us, namely silicon is one reason that we're able to have computers. Silicon is a very important semi-metal because of its kind of properties of being conductive and non-conductive at the same time. We can kind of make it conductive in certain conditions, and so we can have it conduct exactly where and when we want to, which is a very useful property. So semi-metals are going to kind of be intermediate between these, and they can kind of change depending on their situation. So cool. Hooray. Alrighty. We're going to see that most importantly for us, metals in reactions, they typically will form cations. We're going to remember those were positive ions, meaning they will lose electrons over the course of a reaction. Nonmetals, on the other hand, tend to will form anions. Those are the negative ones, meaning they're going to gain electrons. And we're going to look at this in terms of electron configuration. So let's take our favorite metal, sodium, perhaps. Sodium is going to be what? Neon 3s1 for its electron configuration. And if we take chlorine, that's its electron configuration, right? If we were to just kind of cheat that and go real quick with it. If I were to tell you elements want to resemble noble gases, we can see that there's kind of two ways to do it. Noble gases always have a something P6, right? That's what we'll define them as, noble gases. And so we're going to see we have kind of two options. We can either gain electrons or lose electrons. And so if we look at sodium, if it were to want to gain electrons, it would need to gain 7 electrons to resemble argon's electron configuration. Or it could lose 1 electron to resemble neon. And so, just looking at these, hopefully one of them makes more sense, right? It's going to be a heck of a lot easier for sodium to do the bottom one, right? We're going to see it's a lot easier for it to lose that electron here. Let me get rid of that because that's really awful. Let's try that again. There we go. It's going to be a lot easier for it to lose an electron than it is for sodium to gain 7 electrons. Just looking at it mathematically, just totally easier for that to happen. Chlorine, on the other hand, can gain 1 electron to be like argon, or it can lose 7 electrons to resemble neon. And we're going to see that this is going to be the opposite case for chlorine. It's going to gain an electron instead. A lot easier to gain 1 than to lose 7. And so we're going to see that nonmetals will typically be gaining electrons because that's going to be the easiest way for them to resemble noble gases. And we're going to see that metals will typically lose electrons in order to resemble noble gases for the same reason, because it's easiest to get there through that way. All right, if we think about it, when sodium is going to lose its 1 electron, it's going to become a positive ion, right? And we're going to see that the sodium ion's electron configuration is exactly the same as neon's. And this is a very happy thing. Sodium likes this. All the elements like this, in fact. And then when we have the other thing happening, when we have chlorine gaining the electron, that's going to make Cl minus. Cl minus has the same electron configuration as argon. Chlorine is happy there too. So we're going to see that nonmetals will typically be forming negative things by gaining electrons. And we're going to have the opposite case for metals. Well, they will be becoming positive. All right, cool. Any questions so far? I'm pretty silent today. So, talked about metals and nonmetals here. Alrighty, so we're going to see if we take our handy dandy periodic table if we look at our groups, we're going to see that a lot of these groups are going to have similarities in how they're going to be reacting together. If we take a look at everything in group 1, remember everything in group 1, the alkali metals have ns1 as their electron configuration. They want to lose 1 electron. And so very often, in fact, 99.9% of the time, we're going to see everything in the alkali metal group as a +1 ion. You do not normally find these as even neutral compounds. In the video I have, or not the video, in the textbook I have a video of what happens if you have neutral sodium. Sometimes we're going to see that carbon, for example, can go either way. Let's just go ahead and take a look at the rest of these first, and then we'll take a look at that, Ted. So we're going to see everything in the second column is going to form 2+ ions. I should write it that way, shouldn't I? And as we move along here, we're going to see things in the third group, or group 13, or 3A, whichever one you're looking at, typically will form 3+. If we look at group 17, or 7A, those are typically going to form 1- ions. In group 16, you have 2- ions. And then in group 15, you're going to have 3- ions. That's just typically how many electrons these elements are going to be gaining to become noble gases. Right? All of those in group 5A have 3p3 rather. And so they're going to need 3 more electrons to get to 3p6. Or sorry, whatever p6. All right, here you go. Here's our kind of special case. We can see that in carbon's group 14, those can go either way. They can gain electrons or lose electrons. It just kind of depends on what they're put with. If you put carbon with more metallic things, it's going to tend to form a negative ion. Or if you put it with non-metallic things, it's going to form potentially a positive ion, although we see that's less common. So you can definitely have that thing happening there. Yes, there are definitely times where things can gain electrons instead of losing them. Those things are typically not stable. You can end up having positive oxygen atoms or whatever if you're blasting things with X-rays. So you can definitely do that. Can happen, but those things are not going to be very stable. They're going to want to go back if possible. One thing special, by the way, hydrogen can also go either way. Hydrogen can go plus or minus 1. It'll go either way, depending on what it's mixed with. Again, same idea. But everything else in the groups will kind of follow these patterns. I've also put up for you in Canvas as well as on Discord, I've put kind of a little cheat sheet for us. Here, let's go ahead and show the cheat sheet here. Yeah. We're going to see, I've put this little it's going to have a ton of information for this chapter and next chapter. We're going to see here everything in our first group here is going to have those positive 1 charges. Everything in the second group is going to have +2 charges. And then we have our +3s and then our negative 1s here. So we're going to see that that's going to be patterns that we're going to see because these all have the same kind of electron configurations or very similar ones. And so they're going to react very similarly to each other. You're going to see a whole bunch in here. Do not worry, you do not ever need to memorize these, except for the ones that do not have multiple ones. So we're going to definitely want to learn zinc, silver, and cadmium. Gallium, I guess, somewhat as well, but this kind of section here, definitely you'll want to learn them. So, because those will not form different ions. We're going to talk about this sort of thing later on, and we're going to see a lot of these transition metals can actually do, chromium, for example, over here, it says +2, +3, but it could definitely go +4, +6, +8, all sorts of crazy, ions can be formed by chromium. And that's kind of beyond the scope of this class why they do that, but suffice it to say, a lot of these transition metals will do various different things. So we're going to see how we'll figure that out later. On this chart also, you're going to see some common compounds that you're going to want to learn as well. Of course, some of these we know already. There's all of our diatomic elements as well. So your Hofbrinkels there. If we go to the other side, this is entirely everything for Chapter 5A is on this particular page. So everything you see here, let me make this a little bigger. Everything that you need for Chapter 5A is right here. So we're going to learn how to do all these things for naming compounds later on. We're still on Chapter 4, but just kind of a sneak peek. You're going to see here there's a table of what are called polyatomic ions, ions that have more than one atom. You will want to... I can't force you to memorize them because everything would be open book for your exams and stuff. But if you memorize them, you'll have a much easier time. You'll want to memorize not only the formula with the charge, but also the various names that accompany it. So you'll want to do that as well at some point. Especially if you're continuing on in chemistry, you're going to see we use these all the time. And it's going to be a real time drag if you have to go and look them up every single time. So, all right, cool. Let's get rid of this window. So, we're going to see that all of these will tend to react similarly. So, just to write that out, groups tend to react similarly. So that, that just means like all alkali ions or alkali metals, they form +1 ions in compounds. All right, cool. Questions so far? Otherwise, we're going to just look at a few more trends that we can see with the periodic table here, and then we might even start talking about naming things. We'll see. Okay. Alrighty then, let's look at trends in the periodic table. And the first one we're going to look at is size, or something you might see as like atomic radius. So if we were to think about the size of the atoms, let's take a look at our periodic table again. There's a couple of things that we can do to compare a couple of things. So if we look at, for example, fluorine and aluminum and... Wait, aluminum is not there. That's boron. And then, I don't know, lithium. Let's look at those three. And let's see if we can compare them. So, if we just kind of cheat and use our kind of Bohr model here, if we look at the nuclei of these three, lithium, boron, and fluorine, we see that lithium's nucleus is 3 protons, so it has a 3 positive charge. Boron is 5, yeah. And then fluorine is 9 protons, I think. Yeah, 9. And so, if we were to think about these, we have, of course, a bunch of electrons in here that are kind of, setting, or they're the reason that we have, all these various shells and things happening here. 4, 5, 6, 7. Okay. If we want to think about these, those electrons in lithium, let's take a look at this electron in lithium, this electron, and this electron. If we think about how attracted it is to the nucleus, which one of these do we think is going to experience the greatest attraction? We kind of are just looking at our nucleus. We can see that fluorine has a much more positive nucleus than the other two, right? And as a result, we're going to see that this 9 plus will kind of suck in the electrons, because it's so much more positive relative to the other nuclei here. And we're going to see this one is only very weakly attracted to the nucleus. Whereas this one will have a very strong attraction to the nucleus. And this one is kind of, poor boron is just in the middle. So we're going to see that as a result, because fluorine has a much more positive nucleus than lithium, it's going to pull in those electron shells closer to itself, because those electrons are more attracted to the positive nucleus. They're still moving way too fast to actually go into the nucleus, but they're just going to be condensing forward. So as a result, fluorine is going to be smaller than boron, which is going to be smaller than lithium. So for this comparison, the fluorine is going to be our smallest one. And just by comparison, lithium will be our large atom here. And we're going to see that this trend kind of will go throughout the entire periodic table here. We're going to see the left side of the periodic table will be very small, and the right side will be very large. So if we take a look at our periodic table here, we see that size will increase as we go from right to left. So fluorine is going to be very small, lithium is going to be large by comparison. All right, so far so good. Hopefully. Alrighty, let's take a look at lithium versus sodium versus potassium. Which of these is bigger? Hopefully not too difficult of a problem here. I've drawn them, in fact, this way. The more shells you have, the bigger you are. This is the easy one to think about. The more shells you have, the bigger your atom is going to be. That's just how it works. Remember, all these shells build out upon each other. So the farther out you are from the nucleus, you have more shells, you're going to have a bigger atom. And so we're going to see that size will also increase as you go down the periodic table. So this means that francium is going to be our biggest element, right? So francium down here is going to be our biggest element. Has the largest radius of all of the atoms. It has the most shells, and that outermost shell is going to have the very weak influence from its nucleus comparatively to the rest of the ones in its row. So we're going to see as you go to the left and down, you get bigger. And so as a result, you can imagine things are going to be smaller on the top right of the periodic table. So we're going to have helium is going to be super duper small by comparison. If we were to look at number wise, we can see this is going to be the case. Let's see, atomic radius periodic table. Let's have a look here. Alrighty, so if we take a look at some visuals, here are, actually I like this one. Yeah. We can see helium, definitely our kind of smallest one up here. Tiny, tiny, tiny. Oops, don't need this random crap. If we go towards the left here, francium has been omitted. The last row of the periodic table isn't here, but we can see comparatively our bottom left one, cesium right here, is going to be the biggest. So you can see definitely as you go to the left, you get bigger, and as you go down, you get bigger. So here we go. Cool. So a nice trend here. If I asked you to compare things, I'm going to make it easy for you. One of them will be farther down to the left and than the others, so it'll be easy to compare. I'm never going to ask you to compare like gallium and tellurium or something. Like I would never expect you to be able to compare these two. But if you're comparing sulfur to arsenic, you better be able to get that arsenic is going to be bigger, because arsenic is both to the left and down. And you would also be expected to know that phosphorus is bigger than sulfur, but smaller than arsenic as well. All right, so I'm only going to ask you things that are obvious to us. Okay? Cool. Alrighty, let's look again. Another one. How about we look at metallic character? Which elements are more metallic? This one is perhaps even easier. We already know we have metals here, non-metals here, and then kind of the zigzag in the middle, right? That zigzag should hopefully tell us the trend, right? We're going to see that, again, francium down there is going to be our most metallic element. we can see the further up we go, the more likely we are to be non-metallic. For example, here's lead, and here's carbon up here. As we go up, we know lead is metallic, carbon is non-metallic, right? Lead is a metal, silvery gray, hard, dense, can make it into tubes and pipes and stuff, and will typically form positive things. Our carbon typically will form negative things, and it's going to be non-metallic. It's going to be brittle and black and non-conductive and all that good stuff. So we can see from that comparison that as we go down the periodic table, we get more metallic. And we're going to see, if we look at carbon versus lithium, we're going to be more metallic as we go to the left. Just like before. We know lithium, well, you probably don't know this, but lithium is gray and shiny and forms positive things and can be stretched into thin wires and all that sort of fun stuff. Whereas, again, carbon is going to be our kind of non-metal one. And, of course, the further right we go, we notice we become gases. We have the noble gases on the farthest right part of the periodic table. And so those are definitely going to be the least metallic. So, again, francium, most metallic. And then we kind of have fluorine or helium are going to be our least metallic. I'll just, that side of the periodic table. Easy. Alrighty. Let's have another one. We have another trend called ionization energy. And that's the energy required to lose an electron. It always takes energy to lose an electron. And we're going to see that the ionization energy is going to be our way of measuring that. And we can go ahead and look on the periodic table. And so, let's go ahead and take some examples. Let's do lithium and helium. Actually, let's do neon instead, just for the comparison. Okay. Oh, just one electron out there. Oh no. And I'm going to exaggerate this a little bit. Remember, neon is going to be much smaller than lithium is because neon has a much more positive nucleus than lithium. We know that lithium tends to form positive ions. And if we think about it, if something is going to come along and grab an electron off one of these guys, which one do we think is it going to be easier to remove the electron? Remember, this is going to be weakly. Wow, I don't know how to spell. Weakly attracted to nucleus. And these are all tightly held electrons here. Of course, it's going to be easier to remove that electron from lithium, right? Not only is that electron only weakly attracted to the nucleus, because it's far out, it's a big atom, so that electron is really far from the nucleus, and as a result, it's going to be pretty easy to take that. But also, if you take it, you end up making lithium plus, which is going to be stable because it has a noble gas configuration. However, if you try and take an electron from neon, you're going to make it neon plus, which is not something that we see. Not likely to happen because those electrons are already tightly held and it's going to be already stable, so it has no desire to lose an electron. So we're going to see this trend is going to be kind of the opposite one here. We're going to see that the ionization energy will increase as we go to the right. Remember, that's the energy that's required to lose the electron. If it's easy to take the electron from lithium, then it has low ionization energy. It does not require much energy to take the electron from lithium. It's easy to do. However, it's very hard to take the electron from one of the noble gases. And if we compare our lithium versus sodium, for example, oh my goodness. We're going to see that the one in sodium is further away from the nucleus. It's going to be easier to remove than the one from lithium. And as a result, we're going to see that ionization energy will increase as we go up as well. So not only is it up, or not only is it to the right, but also up. So helium will have very high ionization energy. Francium here will have very low ionization energy. Oof, quite a lot of stuff here. So this is the trend that's the opposite as the others. All right, so it's easy to remove an electron from francium because it's so big. You can just go in and pluck that one right off the edge. And there. Hooray! So those are our trends. So I'll just be kind of asking you to compare. Like, let's see if we look at... Let's look at these three elements. This is an example of a question that you would be given. So if we're comparing these three elements, if we want to find which one's the smallest, we have to look at where they are on the periodic table. So sulfur, selenium, and arsenic, let's go ahead and keep those in mind. Let's swap over to our periodic table. We're going to see that those elements are all going to be kind of right here. So sulfur, selenium, and arsenic. All right here. Hopefully you can see where I'm circling. So if we want to see the smallest one, we remember that size increases. Francium is our biggest, helium is our smallest. So that means the top right will be the smallest one. And so of those three, that's going to be sulfur there. Remember, that is that's the highest and furthest to the right. That is going to be the smallest one. If you want to think about what's the least metallic of them, we again will remember that francium, or I guess this UUE thing, is going to be our most metallic. And so again, we're looking for which, if we're looking at least metallic, we're looking the closest one to helium. And as a result, again, that's going to be sulfur. It's going to be our least metallic. And if we're looking at the highest ionization energy, that's going to be, again, helium has the most ionization energy. So again, we're actually looking at sulfur. That's going to be the one that's closest to the top there. And let me add another one so we can actually have a different answer for once. If we look at the lowest ionization energy, that one's going to be arsenic. because it's going to be the furthest down and to the left. All right, so this is kind of stuff that you would be asked. All right. Alrighty, so we have one more. Okay, we have one more bit about electrons. And it'll be the kind of our last little distinction here at the end of the chapter. We're going to see that if we take an electron configuration, I don't know, this will be, I guess, calcium. We're going to see that in the electron configuration, or if we were to write it out all the way, oh my gosh, why did I choose this element then? We're going to see that these electrons are going to have different kind of categories. We're going to see that we're going to call the outermost electrons, we'll call them valence electrons. Those are going to be the outermost shell. The biggest N, so the furthest from the nucleus. On the other side, these guys are going to be called core electrons. And same thing here, we're going to see that this argon, the reason we can do this shortcut is because those all have N of 3 and less. So those are going to be all core electrons. We're going to see core electrons don't really do anything. It's going to be the valence electrons that are going to be doing all of the chemistry that we see. If we look at bromine, for example, bromine is argon 4s2 3d10 4p5. Notice, remember that valence is going to be the outermost shell. So 3d10, even though it is higher energy than 4s, it's still in the third shell. And in this case, because we have something in the fourth shell, the third shell is going to be part of the core. So just note that d electrons are always going to be core electrons. So d and f electrons are always core electrons. Valence are going to be from S and P only. All right, and so if you think about this bromine, we're going to see it has 7 valence electrons. 7 electrons in its outermost shell. And so if we look at our periodic table, apparently we're doing this in light blue, we're going to see that these groups here will tell us the number of valence electrons. And note that the groups are the same name as the number of valence electrons that they have. Or if you're looking at one that has 15, you just subtract 10, and that'll tell you that the valence electrons. So if you ignore the transition metals, if you just label 1 to 8 and ignore the transition metals, you're going to see that the number of valence electrons will just increase by 1 as you go through. Right? If you think about boron here, it will have, let's see, 2s2, 2p1. So it has 3 valence electrons. This is going to be something we're going to focus more on in Chapter 5b, but it's still going to be important for us to distinguish between valence and core electrons. All right, notice that all the transition metals are going to have 2 valence electrons as well, because they start putting things into the d orbital. And remember, d orbital is always core. So all the transition metals will have 2 valence electrons. Alrighty, so we're done with chapter 4. We are going to have lecture tomorrow. We're going to start talking about naming. And we're going to be doing a whole bunch of naming. If you want to look at that chart, that would be a very good idea. If you start getting familiar with those polyatomic ions, everything's going to make more sense to you tomorrow. Yeah, I guess I'll just see you guys then. Don't forget you have some lab sims coming up that are going to be due, and there is a worksheet as well on this electron configuration stuff. All right, so with that, see you guys tomorrow. Enjoy your Wednesday. Take care.